So the second speaker is Maria Arazo Sanchez, and she's going to talk about the chiral state in Bose-Einstein condensates with current density interactions. Please, Maria. We have 20 minutes, yeah? Although we are late.
Okay.
We have.
It works, yes. Well, Egunon, and thank you to the organizers for the opportunity of talking here today. So I will talk about Bose-Einstein condensates with current density interactions. So I will first introduce what these sort of interactions are and which features they have. And then I will focus on two different setups or cases to explain a bit more how they work. First, on a Bose-Einstein condensate in a rotating ring. And then I will generalize this to a two-component condensate. So first of all, just as a reminder for those of you who don't work on ultra-cold atoms, this is the BasQ equation, which allows us to describe a gas of n bosons at close to 0 temperature. So this is the macroscopic wave function. Does it work? The light is not working. The light doesn't work. Okay, well, so we describe the condensate with a macroscopic wave function, and we have to add an external potential. Sorry. We have to add an external potential so the gas is confined and it doesn't expand. And if the gas is weakly interacting and very dilute, we can describe the interactions as effective interactions that are contact and isotropic, which we characterize by this coupling constant that goes with the scattering length of the atoms. And as I said, these are isotropic, local, and contact, very short range. So basically, depending on the sign of the scattering length, we can have attractive interactions or repulsive interactions. So as I said, this works when the gas is very dilute, and actually this equation only works in the mean field regime, which means two conditions. First, that we have a very dilute and weakly interacting gas, so we can neglect quantum fluctuations. And secondly, that the temperature is very well below the temperature for condensation, so we can also neglect quantum thermal fluctuations in the system. So if these two conditions hold, we can consider that there is no quantum depletion, so all the atoms are in the condensate, and we can use this formalism. And this is the condition we will use from now on. And then, since this equation is nonlinear, it supports soliton solutions, which are basically analytical solutions of the one-dimensional Gross-Pitayevsky equation in the uniform case with no external potential. And basically, solitons emerge from the balance between the dispersion and the nonlinearity of the medium. So depending on the interactions on the system, we can have bright solitons if the interactions are attractive, which are self-bound and localized wave packets. Or we can have dark solitons, which are for repulsive interactions, which are density dips, and in general, they are not self-bound. So as I said, the interactions are usually contact and isotropic, but we can have anisotropic interactions in our system that are still contact interacting by using artificial gauge fields. And 30 years ago, more or less, Alietti et al. Described this a chiral theory for Bose atoms, or a chiral theory in general, in which the nonlinearity of the system does not come from the density of the atoms, but from the current density, which is this term here. And they said this theory was chiral because now it breaks the linear invariance, so motion in one direction or the other is no longer equivalent. And one of the main features of this is that we can now have solitons that are chiral, because the interaction is different depending on the direction of motion. So this actually can be modeled in ultra-cold atoms, and this was proposed 10 years ago and experimentally realized very few years ago. And what one does is induce a density-dependent gate potential by tuning the light matter interactions in the system. So one effectively gets interactions that depend on the density, on the current density of the system. And the interesting thing of this presence of artificial gauge fields is that now we can induce electromagnetic-like effects in neutral atoms that otherwise don't behave like charged particles. And as I said, this can be realized in cold atoms, and the experiments that have done since now, up to now, are done with Bose mixtures with asymmetric interactions. So this will be our starting point, this chiral Gross-Pitayevsky equation, when we have this density dependence on the interactions. And this will give a new nonlinearity. Yes, this kappa is a parameter that describes the interactions, and we will set it to positive just for simplicity. And then we can also have contact interactions as in a regular system. As I said, we will focus on chiral solitons. That is one of the main features of this new type of interactions. And well, we can do that with cold atoms. So we will now explore two different cases. First, we will consider a rotating ring. So we have periodic boundary conditions, and now the chirality will come from either counterclockwise or clockwise rotation, or more directions of motion. And we will also assume that the contact interaction is 0 here, because this way we can isolate the interaction, the current density interaction. And then we will generalize this to a two-component system, and we will move to the infinite case for simplicity, and assume that there is no rotation, so we can see how the direction of motion affects in the system without any rotation. So the first case, this is the Gross-Pitayevsky equation with current density interactions and in the rotating frame, where now chirality means going clockwise or counterclockwise. And we can define the conserved energy of the system, where we have where we have a kinetic term, and the kinetic term, and then a second term that couples the rotation and the density dependence of the interactions. As usual, the density of the system and the current density are linked through a continuity equation, and this J omega is the current in the rotating frame. So from now on, we will focus on solitons. So we will consider only stationary states, such that this current in the rotating frame is constant. And the most simple case one can consider are plane waves with a winding number Q. And since we are on a rotating ring, the values possible for this winding number are discrete. And here we calculate the eigenenergy of the system, where again we have this, we plot this as a function of the rotation frequency. And we have a term that goes with the momentum, as usual, a kinetic term. And now we have a term that shifts the energy depending on the current density interactions and on the density. And as we can see, now these energy plots are not symmetric with respect to the frequency as one would expect in a contact interacting like standard case, but they are shifted depending on they are shifted upwards for positive rotation rates and shifted downwards for negative rotation rates. And we can also plot the average momentum, which in this case, since we have plane waves, it's just straight lines. So the next step is to consider solitons. So in general, in free space, we can describe solitons with hyperbolic functions. But now, since we are on a periodic geometry, we need periodic functions to describe them. So we use Jacobi elliptic functions that allow us to generalize the hyperbolic functions to a periodic geometry. And these functions depend, just as a reminder, on a parameter m that goes, when it goes to 0, you recover the trigonometric limit, and when it goes to 1, you recover the hyperbolic limit. And then this is the shape of a dark soliton in a periodic system, where in the right we plot the density profile and the phase profile of this soliton. And then the same for a bright soliton, which the dark soliton will appear for positive frequencies, the bright one for negative, because it's attractive or repulsive interactions. And then besides the density being periodic, we also need the phase to be periodic. And this limits the possible rotation rates. So for each solution with a given number of solitons, we will have just one possible number of one possible rotation frequency. And if we recover the plot from before of the plane waves, we can add these two, this circle and this square, which correspond to the solution with one dark soliton on the right and bright soliton on the left. So what we did after that is, okay, we have plane waves and we have these solitons that exist only for given values of the frequency. So how can we connect between these two sorts of solutions? And I will not go into detail here, just present the results, but we can define a more generic solution that connects between these two solutions. And for example, for positive rotation rates for dark soliton solutions, we can get this line that I added between the red curve and the green curve, which corresponds to a trajectory of dark solitons, of one dark soliton. And here we see that actually if we do the same for a family of two solitons, we can connect plane waves with a difference of j in the winding number when we have j solitons. So this in the average momentum looks like this. So it's a way to connect plane waves, different plane waves with different winding number by solitonic solutions. And one can do the same for negative rotation rates, but here things complicate a bit. If we, for example, consider a family with two bright solitons, we can add this extra line here on the left that connects a family of two different winding numbers with a difference of 2. But for one soliton family, this trajectory detaches from the expected path because now, as we increase the frequency, the interactions increase enough so that the soliton gets to a free particle limit behavior, and it just starts behaving as a particle. So now I will generalize this briefly to a two-component case. And as a reminder, a spinor system or a spinor condensate is basically a two-component condensate where the two components are linearly coupled, so you can have transfer of population between these two components. And these are the equations of motion that we use now, where the psi gives the up or down wave function of each component. And the total density is the sum of both densities, and we need to describe a relative phase, which will be a main parameter in this system. So the parameter nu is the linear coupling, the energy of the linear coupling. And now we assume several things. First, that we don't have rotation because this simplifies calculations. And then we assume also that the interactions on each component will depend on the total density, not on the density of a single component. Because if we do that, then we saw that the energy at the end is not conserved, so we stay with this definition for the interactions. And then we consider we have a large enough ring, so we have an infinite ring with no periodic boundary conditions. So we don't need to use the Jacobi elliptic functions, and this is way easier. So what we did next is, okay, how can we see which quantities are conserved now? And we start with our Hamiltonian. And we do this transformation by adding a phase that depends on the density of the system, which actually is this density-dependent potential that I mentioned before. And then we get this Lagrangian density. And from here, we can calculate the different conserved quantities. For example, the momentum, the mechanical momentum, which has this density-dependent potential included. And then the energy too, where we see here that it no longer depends on the interactions, it just depends on this kinetic term and on the linear coupling between components and the relative phase. And actually this second term is a Josephson-like coupling that measures the spin flips in the system, and it's what prevents the particle conservation in each of the components. But the total number of particles is conserved as expected, and also the alicity is conserved. And this last parameter is what we are working on now to see how this gives the chirality of the state. And finally, what we moved later to do was how to describe bright and dark solitons in the system. So now the chirality will be given by the direction of motion, so the velocity of the soliton is an important parameter. And for negative velocities, we can have bright solitons. which we described in this usual way. And here this is the width of the soliton, and as we see, if we plot the density profile for different velocities, then as the velocity of the soliton increases, the soliton gets narrower, as we expect, because now the velocity increases the strength of the interaction. And on the other hand, for positive velocities, we have dark soliton solutions of this form, where now we have to take into account that the background moves at a different velocity or can move at a different velocity. And again, the width of the soliton depends on the velocity of the soliton. And here we plot the density profile for different velocities compared to the background. So what we see is that in general, the soliton width depends on the velocity, as we expect, because it gives the strength of the interaction. But in the case of dark solitons, it also depends on the sign of on what velocity is bigger, the background or the soliton velocity, because if the background velocity is larger, then the soliton does not get narrower when the velocity of the soliton increases. And this is important because this is one of the main differences with the contact interacting case. And now what we are trying to see is how the spin degree of freedom, because we have two components, changes or adds new physics to the system. So finally, to conclude, I've just talked about Bose-Einstein condensates with current density interactions. And to illustrate how these interactions work, I first explained the case of a rotating ring, where we have seen how plane waves and solitons behave, and also I've presented a more general solution that connects between the two. Then what we did before was generalized to a two-component ring, where the interactions were proportional to the current in each component, but I briefly mentioned that in this case the energy is not conserved. So what we do instead, and what I presented here, is to consider that the interaction in each component depends in the general or in the total current. And so we consider an infinite spinor system. And in this case, we also assume there is no rotation, so that the chirality comes from the direction of motion. And this sort of interactions that I said, and also we calculate different conserved quantities and introduce solitons, dark and bright solitons. And just to end, the idea is now to finish this exploration of the two-component system and also go back to probably the first case of the ring and see how this works more in a more experimental setting where you may have spin flips and how the persistent currents in the ring decay. And then we want to study also how collisions work in this sort of system. Thank you for your attention.
Thanks, Maria. Questions?
Thank you for the talk. I would like to ask, because it's interesting for me, how do you realize this rotation experimentally? Sort of, what are you doing to the atoms in the back to make them rotate, or whatever you want to do to engineer these kind of interactions?
Well, there are several things. So on one hand, this I didn't say where exactly the interactions come from, but these current density interactions, this is like an effective equation at the end. So you first have two components with same species maybe, and different interactions between each component, within each component, sorry. And the idea is that with, for example, Raman coupling, you can eventually end with this model. So, and then there's the rotation on the other hand, which is rotating the trap or something like that, probably.
Okay, just with the potential.
Yeah.
Thank you.
Thank you for the talk. I have a question regarding the dark and the bright soliton. Could you have both in the same ring, or do they have to belong to separate rings?
For example, in the single ring.
Yes.
You could. Yeah, that's one thing we could study how collisions work if you have a dark and a bright, but it's a bit tricky because you have dark solitons if you rotate in one direction and bright in the other, so
Yeah.
that would be problematic. But I guess that if you have the solitons moving in different directions, could be. But
So
you should have something.
If the interaction is repulsive, you could just so a dark soliton could become a bright soliton, and the opposite, right?
Yeah, exactly.
Okay, thank you.
It's a bit tricky.
Okay. So we thank again Maria, and we move to the next speaker.